Everyone thinks a data center runs on its chips, but one dropped packet proves the wiring rules. It can stall a run wiring 100,000 GPUs together. The traffic cop deciding that is a network switch. Here's the part people miss. A training run this size moves in lockstep. Every GPU finishes a step, then they all wait for each other before the next one. The slowest path sets the pace for everybody. So when one packet has to be resent, that adds milliseconds. And at 100,000 idle GPUs, milliseconds are real money burning. So what is a switch physically? Picture a box with dozens of ports, the sockets where cables plug in. Inside is a switching fabric, the crisscross of paths that carries traffic from any port to any other port. Its whole job is forwarding chunks of data, called frames, between the GPU servers. Now an older device called a hub was dumb. Whatever came in, it shouted out every single port to everyone. A switch is smarter. It reads the destination and sends the frame out one port, only the one that server sits behind. Quieter, faster, no shouting. But here's the problem this whole video is about. What happens when 50 servers all want to send to the same one server at the same instant? That's called incest, many senders funneling toward one. 50 cars, one exit ramp. The switch is now a traffic cop at the worst intersection in the building, and how it handles that jam decides everything. So how does the switch know which port is the right one? Every server has a hardware address, a unique name burned into its network card. The switch keeps a lookup table. This address lives behind that port. A frame arrives, the switch reads its destination address, checks the table, forwards it. Simple in theory. Here's what makes it hard. A modern switch does that lookup in a dedicated chip, an application-specific integrated circuit, or a SIC. It's a piece of silicon built to do this one job and nothing else. Why go to that trouble? Speed. Each port might run at 400 or 800 gigabits per second. That's line rate, full port speed, no falling behind. A general-purpose processor reading a table in software would choke instantly. The custom chip makes the decision in billionths of a second, for every frame on every port all at once. Miss line rate by even a hair and frames pile up. And when frames pile up with nowhere to go, that's exactly where a packet gets dropped. Now the collisions. Not wires physically touching, a timing jam. Two streams of data both want the same output port, the same instant. Only one can go out at a time. So what happens to the other? The switch parks it in a buffer, a small pocket of memory that holds packets waiting their turn. Buffers absorb a burst beautifully. For a moment, but a buffer is tiny, and if the flood keeps coming faster than the port can drain it, the buffer fills completely. The next packet has nowhere to sit. It gets dropped. Gone. That is the one dropped packet from our title, born right here. And AI training makes this far worse than ordinary internet traffic. Ordinary traffic is scattered, a video here, a web page there. But when GPUs finish a step, they all swap their results at once, an operation called all reduce. Every GPU talks to every other GPU in the same heartbeat. Synchronized. Bursty. The worst possible pattern for a shared exit, 100,000 cars merging on the same green light. So how do engineers stop the drop? 3 tricks stacked. First, instead of quietly discarding a packet, the switch can tell the sender to pause. Hold on, my buffer's nearly full. The sender waits, then resumes. That's flow control, and the lossless version built for these clusters is called PFC. Nothing gets thrown away. It just gets held. Second trick, warn everyone earlier. Before the buffer even fills, the switch stamps a mark on passing packets, a flag that says congestion ahead. The receiver sees the mark and asks the sender to slow down gently. That early warning flag is called ECN. Slow before you spill, not after. Third and biggest, don't send everything down one road. Between two servers, there are many equal-length paths through the fabric. The switch spreads flows across all of them, so no single link becomes the bottleneck. Spreading traffic across equal paths is called ECMP, and smarter versions steer around congestion in real time. Pause, warn, and spread. 3 defenses so a burst becomes a slowdown instead of a lost packet. Now snap it back to that one dropped packet. Say all 3 defenses fail for a single packet and it's dropped. What happens next? The sender waits for an acknowledgement that never comes. It times out, then resends, but that round trip costs milliseconds. And here's the killer detail. The all reduce we met earlier can't finish until that one packet arrives. Every other GPU is done and waiting on it. So one stalled link doesn't slow one GPU. Because the run is synchronized, it idles all 100,000 GPUs for that entire step. That is the promise from the very first second, now made concrete. A packet you could fit on a fingernail freezes a machine the size of a warehouse. This is exactly why AI data centers refuse to run on best effort delivery, the ordinary internet's shrug and resend approach. At this scale, a shrug is a fortune. They engineer for lossless, collision-free switching instead, because the math of synchronization is merciless. The slowest packet is the whole run speed. So walk the whole path once clean. A packet enters a port. The custom chip reads its destination and looks up the exit in billionths of a second. If the exit is busy, a buffer holds it. If the buffer runs hot, flow control pauses the sender and the congestion flag tells senders to ease off, while the fabric spreads other flows down parallel roads. The packet survives. It's delivered. The training step completes, and 100,000 GPUs step forward as one. Here's the real reveal. A switch's true job was never just moving packets. It's preventing the single drop that would stall everyone. It's a collision avoidance machine. And that's why engineers say the network is the computer. In an AI cluster, the fabric isn't plumbing bolted onto the supercomputer. The fabric is part of the supercomputer. So a network switch isn't a passive pipe. It's a collision avoidance machine working at a scale that idles a warehouse of GPUs if it blinks. But one switch only reaches so many servers. Next, we stitch thousands of them into a single fabric, the fat tree or closed topology, and see how that shape lets any GPU reach any other in just a few hops.